Our next speaker is going to talk about something that has finally made it into the latest DMD, version 2.086, that was just released the other day on the 4th of May. If you've been waiting for the copy constructor, congratulations, it's here. And here to tell you about it, let's hope I don't mangle your name, Razvan Nitu.
That's great. Hello everyone. I'm very happy to be here again at DConf. This year I'm going to talk about the copy constructor, and my talk will progress as follows. First, I'll have the introduction where I'll talk a bit about what copy construction is. Now, I know that most of the people here know this, but if there are any folks that don't have a strong C++ or D background, I just want to make sure we're all on the same page. Then I'm going to talk a bit about the post-blit, and I'm going to highlight its issues. And then finally, I'm going to get to the copy constructor. I'm going to talk about its syntax, the semantics, the breaking changes and deprecations that the copy constructor brings in, and finally, how it can be improved. Then I'm going to wrap up with the conclusions. So, copy construction. What is it? Well, in C, C++, and languages alike, if structs are value type objects. So basically, if you want to, if you have a pointer somewhere and you initialize it outside the struct, if you want to allocate another object as a, if you want to initialize another object as a copy of the first one, then typically the compiler is going to do a byte-wise copy. So you will end up with a pointer that points to the exact allocated memory as the first object. This is what we call a shallow copy. Now, this behavior may be the desired one in many situations, but there are also situations where you would like a deep copy where the allocated memory is also copied. Now, C++ solves this by introducing a special type of constructor, which is a copy constructor that the user can define. It is type checked as a constructor. We will see later what that means. And it is implicitly called in certain situations. Now, another important aspect is that in C++, all structs and classes have a default copy constructor, which the compiler generates if the user does not provide one. Now, let's see what D's take is on this. So basically, in D, the copying is done automatically to a new object, and then control is passed to a function, which is called a post-blit, that adjusts the field that need updating. So, in this situation, let's say that you have more fields with which you are content with normal copying. In C++, you'll have to write this code where you initialize all the fields, although you are content with these fields being byte-wise copied. D speculates this, and in the post-blit, all you have to do is only duplicate S. Now, this sounds really cool because it really saves a lot of boilerplate code. And whenever I tell my colleagues that come from a C++ background about this, they're all very happy about it and they think it's a really cool feature. But the truth is that it hides some design flaws. But in order to understand them, I'm going to delve a bit into the specific of the post-blit so we can all understand them. So this is the syntax. As you can see, you do not have access to the source object, so you can only modify the destination once you get into this function. It does not support any qualifiers, so basically you have only one post-blit function that needs to take care of mutable to mutable copies, const to const, immutable, immutable, and so on and so forth. Also, you cannot overload it, so you have only one post-blit function. And another important aspect is that it is type checked as a normal function. Now I'm curious, how many people in here know the difference between a normal function type check and a constructor type check? Okay, so not too many. Well, it is a very simple difference. So let's say that you have a struct in which you have an immutable field. Typically, in a constructor, you would want to be able to initialize that field. Okay, so here, this assignment is treated as initialization. Whereas, if you're in a normal function, this will be treated as assignment. So you will have an error right here. This is an important difference because if you would not be able to initialize this immutable field, then it would be pretty much worthless. So as you can see here, when I try to modify it, I'm going to get an error because I'm trying to modify an immutable field. Simple, right? Now, with this in mind, I want to show you this piece of code. Now, take a few moments and look at it. And I want to know how many of you think that this code compiles or not.
No.
It doesn't? So how many people do you think that this code compiles? Okay, and the rest of you, do you think that it doesn't compile? Okay, and the rest of you?
Make no bets. I have no.
Okay, but another question, should it compile?
Why not?
I like you, Amori. You didn't get that t-shirt for nothing. Yeah, the truth of the matter is that it should compile. Because we need to take into account that if we'd made a mutable instance here from a mutable x, this would have been valid code, right? But now when we're creating an immutable instance over here, we're basically leaking an immutable pointer to a mutable one. So what happens is that this code is accepted by the compiler. How is it able to do that? It basically casts this object temporarily to a mutable object, so it can modify it here if it's a mutable. So this is pretty bad, and according to the design of the post-blit, this is valid code. Now, since we like the post-blit, we would like to fix this case, right? We want to keep the post-blit. What can we do? Does anyone have any ideas? Yeah, that's true. We can add immutable here. Now the compiler knows that x is immutable, and it cannot assign it to g. However, this introduces some problems. For example, you would need to redesign the post-blit and allow overloads. That's one of it. The other one is that maybe I want to initialize x in my function, right? Because I'm not content with the blitting that the compiler does by default, and I want to update it. I'm not going to be able to do that because the post-blit is type-checked as a normal function, not as a constructor. Now, what would be the logical thing to do in this situation? Does anyone? Yeah, that's the first thing that comes to mind. But you see, when you initialize an object, it needs to be in the init state. After you've done the blitting, it's a bit odd because is the object raw or cooked? And the truth of the matter is that it is somewhere in between. But let's say we make this compromise. We say that the object is still raw, so we can initialize it. Then, what do we do in this situation? So here, we have a struct that has an immutable field and a post-blit, and another struct that contains the other one and also has a post-blit. Now, when this line is executed, what happens is that B's contents are blitted into C, and then A's post-blit is being called. So we're basically we're initializing an immutable field, and we made this compromise, so it's okay. But then, when B's post-blit is going to get called, is this okay or not? Is it initialized or is it not? So we're basically if we make the same compromise again, then we're initializing for the second time a variable. So this is basically, sorry? Oh.
No, I don't want to.
Okay, so this is kind of the brick wall that we've hit. We don't have a solution to this. We don't know how to do it. So we've seen that automatic blitting leads to type check impossibility in the presence of qualifiers. And also, the post-blit still cannot handle copying with differently qualified objects. We took into account this, and it really did the reasonable thing to do was just to drop the post-blit. But if you're not convinced, I want to show you another example. I know that shared is incompletely specified and implemented, but I think we still need to take into account that currently a lot of people are still using shared for structures and in their libraries. So in this example, I have a shared structure. I'm doing a global instance, and then I want to make a copy of it. Now, typically, what the compiler will do is going to blit A's fields into B, and then call the post-blit. Now, what happens if during the blitting phase, a thread comes and modifies the field? So what I'm trying to stress out is that automatical blitting is not synchronized by the compiler implicitly. So how can we solve this? Well, the first idea that comes to mind is to use a mutex, and whenever I want to initialize another shared object, then I can just acquire and release the mutex. Of course, this solves our synchronization problem, but it requires encapsulated attention at each copy site. So it's not a very clean solution. And also, what I want to synchronize is the blitting, because here in the post-blitz, because these variables are shared, they need to be synchronized over there. So ideally, from a performance perspective, what I would want is to be able to just synchronize the blitting phase. So one solution might be to introduce a pre-blit function, where you first acquire the mutex, and then the first thing you do in the post-blit is release the mutex. That way, the blitting is synchronized. But I don't think that introducing more complexity on top of the existing one is the right way to go. Also, we could use an implicit global mutex. Python uses it for their global interpreter lock, but last time I heard they were not very happy about its performance and they were planning on replacing it. I'm not sure what they did in between, but that's also not a solution. So, as you can see, constant immutable post-blitz cannot be safely type-checked, and also shared post-blitz cannot be safely synchronized. Now, these 2 points are all because of the automatical blitting, which seems to introduce, even though it's a cool feature, it seems to introduce a lot of problems. And also, I had to work on this and try to fix the problems, and I can tell you that the post-blit implementation is a patchwork of happenstance semantics. Simply because the design is flawed, there are a lot of situations where the solution is not very clear, and so some hacks are introduced over there. So it just seemed like the most reasonable thing to do was to just drop the post-blit and move over to the copy constructor. Why this? Well, first, because it is a known concept. C++ has been using it for years, and they're very happy with it. The other one is that now that we've lost the automatical blitting, we can type check it as a normal constructor, and we're fine with that. On top of that, we can leverage the existing constructor implementation, which is very robust. And also, it offers us encapsulation by the fact that you can do copies from differently qualified objects. Now, we're very sad because we're losing the automatic field blitting. And some people on the forum said that that's actually pretty bad. But in D, what's the biggest strength of D? Metaprogramming. So this feature is easily replaceable by 2 lines of code. So it really doesn't make sense to try and keep the post-blit because the single advantage of it can be easily replaced. If 2 lines of code is too much for you, we can add it as a library solution and we reduce it to only 1 line of code. And I don't think it can get even better than this. So now, let's talk a bit about the syntax. The first idea that we've had is to use a user-defined attribute and then leverage the existing constructor syntax. Now, the argument is passed by reference because if we would pass it by value, we would need a copy constructor to construct it, and so we will end up in an infinite loop. Also, the argument, the copy constructor, needs to be of the same type of the struct that contains it in order to be recognized as a copy constructor. And as you can see, Q1 and Q2 represent any combination of qualifiers that you want. It can also be nothing. Now, the problem with this is that we're introducing a new keyword, and if you would use this @implicit user-defined attribute in your code, then it's going to introduce some breaking changes. Also, I want to thank Jonathan for pointing this out and for his patience in continuously repeating this. It may lead to bugs, because if you forget that implicit, then your copy constructor is not going to get called. It will be treated as a normal constructor. But we should also look on the bright side, because it doesn't introduce any silent change of code behavior. So basically, that's a copy constructor, and it cannot be a constructor. So what I'm trying to say is that if you define this, if we go this way, there is no way that you had some constructors which before the copy constructor were normal constructors, and then they became copy constructors. And also, it would be easier having this user-defined attribute to spot and differentiate copy constructors from normal constructors. However, the whole idea behind implicit was that at some point we can enhance the behavior so that we would be able to copy construct objects from different types. So from an int or from an t or from whatever. But that kind of feel that we were getting too closer to the existing explicit in C++, where you have this confusion, and whenever you're passing an argument, you don't know, is it a constructor called there or not, and you have to see the implementation. So we decided that we would drop at implicit and simply go with the existing syntax. So this is how a copy constructor looks like. The problem is that it introduces some silent code of change behavior. So if you had this signature in your code, then you will end up with some calls being made to your constructor that maybe you didn't expect. But it can be argued that once you have this signature, what on earth could this be other than a copy constructor? So at best, it can be argued that the compiler is going to fix your code by inserting those calls. Also, it might make some confusion, because if you take a quick look, you might not differentiate between constructors and copy constructors. But it has the big advantage that you don't modify the parser, you don't add any new keywords, and less is more. Now a few examples of copy constructors. This is a very basic one. As you can see, the copy constructor also can take an unlimited number of default parameters. At first, I was opposed to this addition, but C++ does it, so I didn't have a very strong reason against it. If you don't like it, you can just not use it. Yes?
I would say the fact that C++ does it might be a reason against it.
Well, C++ also does copy construction, so. Okay. As you can see, you are allowed to make copies between differently qualified objects. And also, if you're in a templated struct, this is going to be a constructor if you're instantiating with something different than int, and it's going to be a copy constructor if you instantiate it with int. If you want to make sure that in a templated struct you define a copy constructor, then you're going to use type of this, and no matter what you're instantiating that struct with, you're going to be fine.
Question?
Yeah?
Can you go back to the previous slide, please?
This one?
Yeah, in the bottom you'd say type of this. Well, D has a shortcut where you can just use T there.
Oh, okay. I have to admit I didn't know about that.
Yeah, what? Yeah, T works as a template because it expands to that particular instantiated type if you just use the template name by itself. So it's actually it's simpler than typing in type of this. You can just go T and it'll work.
Yeah, that's cool. I was thinking that if you have a lot of code and the copy constructor somewhere around the lines of it, if you see type of this, the intent is clear. If you see T, you have to go to the declaration and see. Yeah. Well, anyway, you can use it however you want. So other properties of the copy constructors, they can all be called on L values because you're taking a reference, so you cannot take the reference to an R value. I know there is ongoing work on binding R values to L values, but that's beyond the scope of the copy constructors. Copy constructors can also be explicitly called. So besides the fact that there is no reason to forbid this, there might be code out there that has explicit calls to copy constructors, so we don't want to break that. Copy constructors are type-checked as normal constructors. I've already said that. Also, you cannot template copy constructors, since you have the rule that the type of the parameter needs to be the same as the struct that's containing it. It really doesn't make sense to offer this possibility. And since most of the time the compiler is going to insert calls, I couldn't find the reason why I would, yes? Template this parameters?
Since copy constructors can have any number of default parameters, why can't you template those?
Well, when I initially designed it, I was thinking that the copy constructor was only going to get called implicitly. So since you cannot do that, oh, yeah. Oh, you're right. I just didn't take too much into account the fact that people are going to explicitly call that copy constructor.
Okay.
I thought you were going to ask about template this parameters.
That too.
The answer to this is that we have in-out, so we can declare in-out copy constructors, which would achieve pretty much the same effect. And also, copy constructor calls are going to get inserted implicitly in certain situations, which we will now see. So the most basic cases where you explicitly initialize a variable, so the compiler is going to insert a call to this copy constructor. When you pass an argument by value, again, the copy constructor is going to get called. And also, when you return by value and no optimizations can be performed. So there are situations where copy constructor calls can be elided. For example, here, where name return value optimization is performed, and this object is directly constructed on the stack of main. As I've said, the copy constructor can be overloaded. The overloading is based on qualifiers. For all intents and purposes, if you have code out there that uses the post-blit, you can first, if you want to transition to the copy constructor, the first thing I recommend you do is just try to replace the post-blit signature with this one. Of course, given the fact that the post-blit is flawed, it might or might not work. And I've just realized that I forgot to include this in the presentation, but the compiler with the post-blit, it did some OP assign generation. So in some situations, it generated OP assign based on the post-blit. Currently, there is no OP assign generation depending on the copy constructor. So that might be a problem if you are relying on that in your code. Also, you can disable copy constructors as opposed to the post-blit, where you could just define the single post-blit overload to disable copy construction. Here, you would have to disable all the overloads of the copy constructor to achieve that, but it can be simply done by doing a disable block for all your copy constructors. Or you could just define the basic copy constructor and annotate it with disable if you previously didn't have any copy constructors. Now, let's talk a bit about blitting. So if you don't have a post-blit or a copy constructor, the compiler is going to do implicit blitting. So here it's not like in C++ where you always have a copy constructor. If you do not have any copy constructors, that means that the compiler can freely blit your objects. So in this situation, as you can see, there is no post-blit or constructor, so anytime you do initialization by copy, be it mutable or immutable, the compiler is going to be safe to do mem copy. Of course, it has to be of the same type, so you're not going to be able to, for example, to do blitting in this situation to a mutable object from an immutable one. Now, what happens if we have a copy constructor? What should the compiler do now? I'm talking about here it's fine because we have the mutable to mutable one, but here we don't have an immutable to an immutable. So there are basically two things that we can do. One strategy is to try and use a copy constructor when there is an available one. If we do not have one, then we can attempt to blit the field. If that also fails, then we're going to issue an error that we don't know how to construct that object. This has the advantage that if you have, let's say, an object where you're content with the implicit blitting, but you want to be able to define more curious cases where you want, for example, to construct an object, a shared object from an immutable one, or a const in out, whatever, to a shared something, then you can just define the only copy constructor that interests you. But it has the disadvantage that it cannot work with reference counting. For example, if you want to implement a reference counted object and you define, let's say, 15 copy constructors and you forget to define the immutable to immutable one, once you try to do initialization by copy, then the compiler is going to go behind your back and do some blitting, and your reference count is going to be corrupted. And as Walter stated, reference counting is the canonical example for copy construction. If we have failed to implement reference counting with the new copy constructor, then we can assume that we have failed. The other strategy is that once a copy constructor is defined, all blitting for that struct is going to be disabled. Of course, this is good for reference counting because if you forget to define a copy constructor, once you want to call it, you're going to get an error. But it also has the disadvantage that you need to define a lot of copy constructors. But I think that the argument here is that once you have defined the copy constructor, you cannot simply assume that in some situation it's fine to do blitting, while in others you need the user to help you. So in this situation, you're going to get an error. Copy constructor generation. Now, if a struct does not explicitly declare a copy constructor, and that struct has at least one member that has a copy constructor, and that member is not overlapped, then the compiler is going to generate this copy constructor for you. It is in-out because, as I've said, it is recommended that you try and replace your post-blit with an in-out copy constructor. So if you have it, then the compiler is going to generate one wherever you use that struct, and this is going to be correctly type-checked. Of course, if you do not have an in-out copy constructor, the compiler is going to generate this, but is going to fail to type-check. Now that we've talked a bit about the post-blit, how can the post-blit and the copy constructor cohabitate? Well, the answer is that they cannot, because they do the same thing. So if you have them both, the compiler will not know which one to pick. But in order to assure a smooth transition from the post-blit to the copy constructor, the convention is that whenever you have a post-blit, all copy constructor definitions are discarded. Beware that if you have any fields with post-blits, the compiler is going to generate a field post-blit for you, and that may invalidate your copy constructor. So if in your situation where you have a class with some members, a lot of members, and you have a copy constructor and it's not called, then most likely somewhere you have a post-blit. Of course, the copy constructor introduces some breaking changes, and one that was talked about a lot in the forums was the fact that you can pass a mutable source. So basically, you can modify the source in your copy constructor. The argument to this was that C++ does not allow it. I want to say that this is false because C++ does allow mutable sources. It's just that it is heavily discouraged. The other argument for this is that qualifiers in D are transitive. So if we would require that we have const here, then we couldn't do this assignment over here, so we would need to cast it and make the copy constructor unsafe. So we consider that it's fine. If you don't want to have a mutable source, then just make it const and deal with the consequences. The other breaking change is that if you had this signature in your code, then before dispatch, you would not have any call to a copy constructor, while after this, the compiler is going to insert a call to this copy constructor. But again, I would argue that that is the correct behavior, because if you forgot to call your copy constructor here, then most likely you had a bug in your code. Now let's talk a bit about how we can improve things. So what I've talked about until now, you have it in the latest release of DMD. So we can do smarter generation of copy constructors, and also we can try to generate OP assign based on copy constructors. Now, let's take a look at this example. So if you have a struct that knows how to create an immutable copy from a mutable one, and a struct that knows how to create both an immutable and a shared copy from a mutable one, and then we have one that aggregates the two. What is the compiler going to do today? It is going to generate this copy constructor. It's not entirely true that it is going to be generated like this, but for all intents and purposes, it is something similar. Now, what can we see over here is that this is going to fail to type check, and this is going to fail to type check because both A and B do not have an in-out copy constructor. So the compiler is going to annotate this with disable, and basically it says we don't know how to copy construct C. I would argue that since A and B both know how to create immutable copies, then we can try to generate both an immutable and a shared copy constructor. And since the one is going to be successfully type checked, we can use it. But this cannot be successfully type checked because this line is going to fail because A does not have a shared copy constructor. So we've gone from not being able to copy construct an object to being able to copy construct in some situation. So I would argue that this is a better mechanism. This can be easily implemented by having a hash table which tracks the types of the copy constructors that you define, and then try to generate all of them and then type check them and see which one can be used and which one cannot. Okay, op assign generation. This one is a bit trickier. So in C++, practice has shown that in some situations, the copy constructor and the assignment operator both have the same body. So it would be really cool if we would not make the user offer them both when a copy constructor is sufficient. So in able to do that, we would require that the struct does not have any constant immutable fields. Why this? Well, then the struct is not assignable. So, and there are some deeper reasons. For example, the copy constructor is type checked as a constructor, while the op assign is going to be type checked as a normal function. So basically, if you have a constant immutable field, the copy constructor is going to be able to initialize it, while op assign is not allowed to modify those fields. The other thing that we do, of course, we need to have a copy constructor that creates, first we have to have a copy constructor, and also it has to create a mutable copy, because if it does not create a mutable copy, then I would argue that those are odd situations. So if you want to have an assignment operator that creates an immutable copy, it would be better that the user define that, because you cannot know what the intent is. And also, we want this because we want the signature of op assign to have an argument which is taken by a value, because that way I'm going to be able to call the copy constructor. So once op assign is going to get called, you would need to create this object, and then if you do not have a destructor, you can simply blit the contents of S to this and return it. If you have a destructor, things get a bit more complicated because you might be implementing reference counting and you need to implement the destructor. So what have we done here? Once op assign has copy constructed this object, we're going to make use of a temporary on which we are going to blit the contents of this, so no op assign, no copy constructor is going to get called here. Then on this I'm going to blit the object I just copy constructed, and then I'm going to call the destructor on the temporary. It should be noted that this argument, this is implemented with a bit of compiler magic, where this object is not going to get destroyed, because it might have some references in there to allocated memory, and if I'm destroying this, then basically I'm invalidating the copy that I made. What I want to say is that I didn't invent this. This is already being done for the post-blit. So I see no reason why we cannot leverage this and also implement it for the copy constructor. I guess that an argument can be made that I know some people that are not very fond on the compiler generating operators for them. But I guess it's still an open discussion. Now, the conclusions. D now has a copy constructor. It is very similar to the C++ one, but it can also be improved. Now, if you're interested in more details, these are some interesting links: the DIP, the documentation, and the implementation. And now, if you have any questions, feel free to ask. Yes?
Yeah, so first I would want to apologize if those matters have already been discussed, because I've not been following the online discussion about this matter. So maybe I'm just like rehashing some stuff that have been discussed to death. So the first one is, okay, currently I'm working on a code base that has a fair amount of C++, and we went through a very painful process to mark all the constructor explicit in C++ because we had a bunch of copy that were just using a bunch of cycles that we don't want it to have. And so we wanted to make sure that those copies are actually explicit. And the way I was proceeding in D before all of that is trying to make the struct non-copyable. And then I can, call a constructor that does the copy, essentially like a copy constructor, except it's not like specifically understood as a special kind of constructor by the compiler. And the problem I run into with this approach is that generally, like, disabling copy of struct is very buggy, very badly enforced. And so I'm wondering how much, like, all this new stuff is added to work around things that we were supposed to have that don't work quite right. And that's a bit of a concern to me. The second point I would like to bring is that it seems to me that from the current post-blit definition, it would be actually possible to change the semantic to make that a copy constructor in most cases. Because you can do essentially a flow analysis on the function and not blit anything that is assigned in there. And anything that is assigned in there is essentially considered like you would consider it in a constructor. And so I was wondering, like, if that approach was considered, and if so, why it was rejected.
Well, not really, because currently DMD does a very basic flow analysis. So in order to do what you proposed, that would require some advanced techniques, even for the simple cases, but for corner cases that would just get horrible. So Walter is usually against adding new complexity in the compiler. So what we have now is just, we have this robust implementation of constructors, and we want to leverage that wherever we can. We don't want to introduce new complexity. We don't want to introduce advanced data flow analysis on the instructions. I hope this answers your question.
I can take the first one. So the explicit constructor issue. So this actually is not weakening, is not making the constructor any more trigger happy than it was in D. That was a problem in C++ that we avoided from the get-go in the D language. So the good news is you're not going to have this problem. The problem in C++ was that if you don't make your constructors explicit, you're going to have odd cases accepted, like, you define some class C, and then you say C x equals 1, and all of a sudden 1 would be converted into the class object because you forgot to put explicit in there, and that most of the time is undesirable. In D, you would always need to actually construct explicitly the object. So that's not an issue, and it's not going to become an issue after this dip. With the second, Razvan and Walter and myself, we've been discussing several times, and the community also has been privy to many of these discussions. Essentially, at some point, maybe you can do something just because you can, it doesn't mean you should. Converting the post-blit, making a type, a semantic check that works for the current post-blit would have been a Pyrrhic victory at best. So assuming we did to perfection, it would have been extremely difficult to explain to anyone what happens for any given code base. So we thought a clean slate is the best choice in this situation.
So adding on what Attila asked about templatizing the copy constructor, so I've been thinking about there could be cases where you already have a templatized constructor which would basically fit the copy constructor, but as you explained, it would not be considered a copy constructor at the moment. So this kind of seems like an arbitrary limitation to me, because it could be considered a copy constructor if the correct type is used. And there could also be cases where like the implementation or the generic implementation of a constructor and the copy constructor implementation would be the same, so I had to duplicate this code. So I don't really understand where this limitation comes from.
Well, first you can instantiate your constructor in the copy constructor, so that might be a solution. The other thing is that a copy constructor, since it's going to get implicitly called, in some situations it might not be able to deduce the types to instantiate a template. So now that you are highlighting this, I can think that it can be template. Maybe a copy constructor can be templated, and if it can deduce its arguments from when it is implicitly called, then it should be allowed. But the point here was that we wanted, since we had these problems with our post-blit, we wanted to have a wiser approach in which we just implement what C++ does, and then we are able to add some enhancements.
Okay, thank you.
So today with a post-blit, if you want to make a type not copyable, you disable it.
Yes.
How do we do it now?
You disable all the copy constructor overloads.
Okay, but is there a transition period in which I have to disable both, or?
To disable
The post-blit and because the post-blit still exists right now.
Yeah, but if you have the post-blit, the copy constructor is going to be ignored. So you cannot have both. Maybe I'm not understanding your question.
Well, I'm trying to make the type not copyable. Right now, all I have to do is disable this.
Yeah.
So.
Now, if your code base has both post-blits and copy constructors.
No, but it doesn't have either. I'm trying to make it not copyable.
Yeah, so you need to disable all the copy constructors.
Okay.
All of them?
If you want.
If you want to make a struct not copyable, you define one copy constructor, and it doesn't even matter how it's qualified, and you mark it as disabled. And then you can't copy it. I wish to point out a subtlety that may have been missed, is D always had copy constructors. It's just that you have to use them explicitly. What this change does is make them the same copy constructor now implicitly callable. And so it's really not a big change to think, because it was already there. It just now it happens implicitly, and you get the auto generation of copy constructors if they weren't there before. So you may have already, and sort of that answers the question of what happens if you have both copy constructors and post-blits. What you get is the old behavior. If you use the copy constructor explicitly, it will call the copy constructor just like it used to. It just won't call it implicitly if you have a post-blit anywhere in the in your data structure.
Is there a plan to deprecate and remove the post-blit?
On the long term, yes, but on the short term, not that I know of.
It'll be like the C preprocessor in there forever and annoying people. So, but yeah, with the introduction of the copy constructor, you know, everyone should just, even though the post-blits are going to be there for a long time, I recommend that you abandon them and delete them and replace them with copy constructors as you run across them. And your code will be better off and more modern as a result. But there doesn't seem to be a pressing need to actually remove them from the language and break working code. The post-blit's a little weird, its syntax is a little weird, and it can, I think, be safely left in the language. If it causes any trouble, you'll get compiler errors from it. So I don't think it's a big deal to leave it in. In that way, it's not like the C preprocessor, which seems to be troublesome even if you try to avoid it. So the idea is we want to keep existing code working as long as possible, but you should still migrate to using copy constructors.
We have one more question.
Well, something I thought of, if somewhere in your data structure there's a post-blit constructor, then the copy constructor doesn't get called. But what if you use a library from DUB which has a post-blit constructor, then you cannot migrate to copy constructors. Am I understanding this correctly?
I think that what you can do, you can disable your post-blit. So, so you're talking about using a struct that's defined in a library, right?
Yes.
Yes, the library owner needs to update their code.